The first question, number 13, this one, the answer is 8. Yeah. 8 multiplications, the answer. Yeah. And not many students got this one. Yeah. Yeah. Most students got much more than this number, but a few students got a 6. Yeah. Yeah. All right, so let me explain how to solve it. Yeah. The first thing, first common problem you should avoid is, so this is a big problem. Yeah. The first one, do not expand the polynomial. Yeah. A few students expand the polynomial, then count the multiplication. In that way, your multiplication number of multiplications is much bigger than what we have without expansion. Yeah. So here the reason is very simple. So here let me explain the reason. Yeah. We know expansion. Yeah, because many people tend to do expansion. The opposite of expansion is factorization. Right? Yeah. The opposite of expansion, factorization. And we know why Horner's rule is so fast. The Horner's rule takes advantage of factorization. Or in other words, factorization helps us to make the computation fast by reducing the number of multiplications. So that's the key to the success. Factorization is the key to the success. All right. Now you go opposite way. Okay? You go opposite way away from key to the success. Okay? Yeah. So that's why your number is large. Okay? Large number of multiplications. You go the opposite way, okay? You go the opposite way. Yeah. Don't do it. Yeah. Because usually, in order to reduce the number of multiplications, the first method we want to try is try to factorize it. If you can do factorization, you want to do factorization as much as you can. Yeah. So that's our understanding of the Horner's rule. Okay? Yeah. Never go opposite way. Opposite to the factorization. That's the expansion. Yeah. Yeah. As a result, you can see if you apply the expansion, your multiplication number is very large. Yeah. All right. So next, without using the expansion. Yeah. Then, let's calculate each one. The first one, by Horner's rule, the degree number, right? The Horner's rule, degree number, so this is degree number. So 2 multiplications. And for second one, Horner's rule, 2 multiplications. The third one, still Horner's rule, 2 multiplications. Yeah. But I saw a few students, for each parenthesis, each pair of parentheses, they didn't apply the Horner's rule. They just count the multiplication directly, so that they use 3, 3, 3. Okay? If when you count the the number of multiplications for 3 pairs of parentheses. If you use the 3, 3, 3, then that means you didn't apply the Horner's rule. Okay? If you apply Horner's rule, you use 2, 2, 2 multiplications. Yeah. All right. Then the last two, you need to find a product of all these numbers. The 3 per pair, so 2 more, right? After that, you need to do 2 more. And I thought those students who gave me 6 multiplication, they didn't count the last 2. They didn't count these last 2. Yeah. 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 So that's the right way. So that's the reason we get 8. Okay. Yeah. 2 plus 2 plus 2, and plus the last round, another 2. Okay, yeah, so you get 8. Yeah. All right, yeah. That's this question. Yeah. Next question, closely related, but we can set our starting point as the previous question, right? Oh, okay. Yeah, no problem. Yeah, what's your question? Yeah. Correct. Oh. Uh-huh. Just a minute. For the first parenthesis, how many multiplications you need for the first? Only look at the first parenthesis. How many you need? 3. All right. Yeah.
Well, you need 1 to get x squared, no matter where you're at.
Yeah. Correct. Yeah.
So if you do that outside of the parentheses, you do inside.
Yeah, inside. We only look at inside parentheses. Yeah, outside we do later. Oh, outside you do 2.
Inside you do 2, assuming you already have x squared.
Oh, now I understand. Yeah, all right. Yeah, okay. Yeah. So you said we already have x squared, right?
Yeah, we already have x squared.
Okay, x squared. All right. But the first one, you need to calculate it, right? X squared. The first time you need to calculate x squared. Do you need to do this multiplication? x2 times x squared? Do you need to do x1 multiply x? Yeah, right. So if you do this one, you didn't apply Horner's rule. Okay? You didn't apply Horner's rule.
Apply Horner's rule.
Right. Apply Horner's rule inside each one. You get 2. You get 2. Right? Yeah. So here, yeah, after this class, yeah, because your habit, your old habit still very strong. Yeah. For many students, your whole old habit without using Horner's rule. Yeah. Because Horner's rule is new for you, very strong. So after this class, you need to, whenever you need to evaluate polynomial, you always need to think about Horner's rule. Yeah. Horner's rule. And you just memorize the result of Horner's rule. The number of multiplications you need is the same as the degree number. Yeah, because why I ask you memorize this result? Because some students, it's hard to recover the details, right? When we talk about Horner's rule, it's hard to recover the details. Yeah. So you don't have to recover all the details. You just memorize the result of the Horner's rule. The same number of multiplication as the degree number. Highest degree number. Yeah. The degree number. Yeah. Degree, we mean the highest term. Yeah. Degree term. Yeah. Then, yeah. so you can understand. So you do not need to, going through. So think about, so actually you're going through this our same discussion before the break, right? Before the break, I try to explain 4 multiplications. So actually here we go the same path. Same path, yeah. All right, yeah. Good, all right, yeah. So hope you get stronger impression after this discussion. Yeah, everyone got a stronger impression. And don't forget, in the midterm questions, try, whenever you see polynomial evaluation, yeah, try to connect to the Horner's rule. The first thing you do, connect to the Horner's rule. If you forget that, then it's very likely your answer is much worse than the correct one. Yeah. All right, let's move to the next question. Next question. Our starting point is the previous question. So we do not need to do things from scratch. Okay. So what do you mean? Our starting point. Our starting point, let's write this polynomial function as a0 plus a1x plus a2x squared. Yeah, you mean the whole thing I just copy. But I take the 5th power out of the big brackets, big pair of brackets. How about this? Okay, inside brackets, using the result from the previous question, 8 multiplications. So we do not need to redo it. Okay, yeah. All right. So then, the same number raised to, yeah, so here. So if I use y to represent this number, okay, inside the brackets. So p of x, I just do the y to the 5th. Y to the 5th, can we write as y squared times y? Okay? Yeah. So that's 3 multiplications. Repeated squaring. Yeah. So you're familiar with that. Okay? So the total 8 plus 3, 11 multiplications. Think about that. Okay, 11 multiplications. Yeah. All right. Yeah. Here, as a practice, yeah. So because most of you missed these 2 questions so much, so definitely I will give you similar questions, similar to these 2 questions in the midterm. Yeah. So try your best to understand these 2 questions. Then using the same way to answer the those 2 midterm questions. Yeah. Here I like to give you another example, similar example. I just modify a little bit. Yeah. The first parenthesis, I want to use a variable u to represent it. Because in that way, I do not need to copy. When I copy the whole formula, it takes quite some time. Okay. Second parenthesis, I want to use v to represent it. The third, w to represent the third parenthesis. All right. Now I ask you to calculate this polynomial. Sorry, the polynomial, the structure is, say, x, not w. Yeah. The structure is U, I put a square. V, I put a fourth. W, I put eighth. Yeah. If I ask you to calculate the minimum number of multiplications for this structure, how do you use the minimum number of multiplications? Yeah. This structure. Yeah. Yeah. U, V, W, they have different exponent numbers. Yeah. But here I give you, 248, 248, some special exponent numbers. So you try to take advantage of these, special numbers. Yeah. Try to minimize the number of multiplications. Yeah. Here, the way to minimize it. Yeah. Yeah. So we just count the multiplication after we get a U, V, W. Okay, U you need 2, V you need 2, W you need 2. Okay, after that, yeah, how many more we need to get the final product? Yeah. All right. Look at the structure. So that structure we want to write this way. All right. Yeah, because first the exponent number, even number, right? Even number, yeah. So here, I want to talk about the idea. Yeah. Remember, I mentioned idea before the break. We talk about Horner's rule. I mentioned one idea, share multiplication, right? Yeah. So before the break, yeah. So before the break, I talk about the idea. Okay, so factorization allows us to share multiplication among terms. And in this way, we can reduce the number of multiplications. Here, we want to extend this idea a little more. This time, we do some special operation, okay? Some special operation. Special operation helps us to share something. So share what? Share square up, okay, among terms. How about that? Because these numbers we can connect to square operation easily. Okay, share square. So let's do the square sharing. Okay, square sharing. All right. P of x. First square sharing. U times V squared times W fourth outside one common square. How about that? Okay. Individual square we make common square. So to save multiplication. Yeah, but that's the first round sharing. Yeah. Then if we look at these two operands, we have second round square sharing, right? So let's do second round square sharing. U times V times W square, common square, common square. How about that? Okay? Yeah. Yeah. Now, when you count, yeah, so 1 multiplication here, w squared, times v second one, then square third one, fourth, then fifth. Yeah. Is it too many? Yeah. Yeah. Is it too many? Yeah. Yeah. Anyway, so here I give you the idea. So I will double check. Yeah. If this is too many. Yeah. All right. So so you just get the idea. So if we can share some common operation, yeah, common operation, then we can reduce the number of total operations. Yeah. Yeah. All right. Yeah. So let's move to the next question. Yeah. Yeah. This one. Most students give me the answer 10 by repeated squaring. Okay. Most students give me the answer 10 by repeated squaring. But that's not the best answer. Yeah. If we can mix repeated squaring with repeated cubing, we can get better. We can get 8. Yeah. We can get 8 multiplications by mixed. Some places we use repeated squaring. Some places we use repeated cubing. So this question I want to address that problem. And repeated cubing. How do you see it? Yeah. So you may ask me, how do I know I need to mix repeated squaring and repeated cubing? Yeah. So here, look at this 33, this special number. This special number 7 times 9. This 9, you see, it's a 3 square. 9 equals 3 square, power of 3. Yeah. Yeah. If that number gives you a lot of power of 3 factors, then it's very likely the repeated cubing can do better than repeated squaring. Okay? Yeah. Yeah. Right. So here, yeah. So let's try repeated cubing. Yeah. Repeated cubing, yeah. So the first round, let's do repeated squaring first. First round. Okay. Yeah. So we calculate x squared, x to the 4th. Yeah. X squared, x to the 4th. Okay. Yeah. And then x to the 7th equals x to the 4th times x squared times x. Okay. Yeah. So one multiplication, the second multiplication, yeah, 2 more. So for x to the 7th, you need 4 subtotal. Okay. Multiplication. That's the first round. Then second round. Second round, you need to switch to repeated cubing. Yeah. Yeah. Because so many power of 3 factors you need to take advantage of. All right. So then 7. Right? Yeah. X to the 21st equals x to the 7th times x to the 7th times x to the 7th. Okay. Yeah. 2 more multiplications. Then x to the 63rd, x to the 21st, x to the 21st, x to the 21st, and 2 more. Then you add up total (4 plus 2 plus 2 equals 8). Yeah. And some students give me the different way to get 64. That's okay. Yeah. I saw one student give me, use this structure. 27, x27 times x27 times x9. Yeah, that's also fine. You get the same number of multiplications. Yeah. Because that student, you can calculate. Yeah. Oh, in this way, you only need to use repeated cubing. Okay, this way only repeated cubing. You do not need to use repeated squaring. Also correct. Okay, yeah. So think about this. You need a 4, right? You need a 4. And from x to the 9 to 27, then you need one more. Okay. Yeah. Oh, you need a 7. Yeah, because 2 more. Sorry. Yeah, because you need a cube operation. Cube operation, you need 2 more. Right? Yeah. Then 1, 1. So the total is also 8. Yeah. This way, the total also 8. Yeah. Yeah. So from this example, so you can get an idea. Actually, I mentioned this result in the class. When we evaluate a general monomial, x to the n, the general monomial, sometimes the repeated squaring gives you the best solution. Sometimes repeated cubing gives you the best solution. And sometimes you mix repeated squaring and cubing, you get the best solution. Okay? You mix, but get the best solution. Yeah. Yeah. Right. Yeah. Yeah. All right. So let's just move to the next question. Yeah. What about? Yeah. Oh, yeah. Good. Yeah. So Sam, yeah, if you wrote that way, you need a 10, right? So Sam, you wrote that way. Yeah. So that's the way. That's the yeah. So, because the way you wrote there, that's the repeated squaring. So you wrote this way. 32. To get 32, you already need a 5 multiplication, right? So you multiply. Yeah, so let me copy 16. Yeah. Yeah, because 16 you do not need a new, you already cover it. 8th, you already cover it. 4th, you already cover it. Square, you already cover it. Right? And x. Yeah. Look at how many dots you have. 1, 2, 3, 4, 5 dots. So the preparation step, you need a 5. Then the second round, you need a 5 more. So you get 10 multiplications. It's bigger than this new method, right? New method, we need 8. So the old method, you need a 10. And we should choose the one with the minimum number of multiplications. Yeah? So that's the reason most students give me question 10. Yeah. So is it a rule if you get multiple of to be 3 to the power of something you can use? Yes. Yeah. Yes. That's what our experience. Yeah. So what you observed here, that's our experience. Yeah. Yeah. So if you see a lot of multiple of 3, so then it's very likely repeated cubing can give us better solution. Yeah. Yeah. Yeah, but sometimes you cannot see 2-factor, 3-factor. Yeah. So then it's hard to say. Then it's hard to say. Yeah. Yeah. But we can design an algorithm to find the best solution. Yeah. If sometimes we cannot see which one clearly better than the other, yeah, but we need to rely on our program to tell us which one better. Yeah. So last semester I assigned this problem as an optional extra credit problem last semester. This, because this semester we run out of time quickly, so I do not have time to assign you, more questions like this. Yeah. So I skip it. Yeah. Okay. Yeah. All right. Yeah. Let me move to the next question. Yeah. Yeah. This one, yes. First, let me tell you the answer. Then I explain it. Yeah. Because there are so many different answers, but there is some common mistake. Yeah. I want to explain. Yeah. So the answer. Yeah. First. Yeah. The first thing you need to know. Yeah. When we count, so here, let me talk about general question. Yeah. So when we count the number of global inversions. Okay? Yeah. Because several students only count the number of local inversions. So that's a very small number. Yeah. So here, because here the question does not say local or global, then we mean global. Okay? No. Then we mean global. Yeah. If we do not say explicitly local or global, then it must be global. So that means all kinds of inversions must be considered. Yeah. So you cannot restrict yourselves to local inversions or adjacent inversions. Yeah. All right. So when we count non-inversions for n element array, there is a general formula. Okay, general formula. So here, if I draw a diagram a little bit, yeah. Diagram. So x1, x2, x3, xn. Yeah. Because here we want to consider the maximum number of inversions, the maximum. Number of inversions. Yeah, because our question, we look at the maximum number of inversions. So maximum, we assume between every 2 pairs of elements, there is an inversion. So for x1, with, starting from x1 and all the possible pairs, we have inversions. So from x1, starting from x1, we have n minus 1 inversions, right? Starting from x2, x2 is the first element in the pair. So we only look at the x2 with the element after x2. So n minus 2 inversions, and so on. xn minus 1, 1 inversions. xn minus 1, only 1 inversions. Then the total number of inversion. That's the maximum. 1 plus 2 plus dot 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 plus n minus 1. That's we know the formula, 1/2 times n minus 1. Okay? All right. So this is the general result. Okay? So before you answer this question, you should know this general result, so that we can apply it. Now, but for this question, there is a condition. It is known that x sub 9 is not in place. Okay, this condition, not in place. Yeah. So we know its meaning, in place. So if we, if we sort it, x9 is at the right position, that's in place. But here our assumption, x9 cannot be in place. Okay? Yeah. All right. But this condition, when we do the counting, if we want to factor in this condition when we do the first round counting, factor in it in our first round counting, usually hard, right? Yeah, usually hard. Okay? Yeah. So remember, in problem solving, when we work on a version of problem that is relatively hard, we should solve a simpler version first. Remember, I mentioned this strategy before. Yeah. So we want to work on a simplified version first. So here, the strategy. Okay? Our problem solving strategy. When this problem is relatively hard to solve, so we work on a simpler version of the problem. Yeah, version. Okay. Simpler version of the problem. Yeah. So what's the simpler version of the problem? Let us erase this condition. Do we make the problem simpler if we erase this condition? No, because this condition, if we factor it in, we need to take care of more things, right? We need to do more work because we need to take care of this condition. So we need to do more work. More work means harder. This version is harder. So now we want to make it simpler, so we remove this condition. Then we do not need to, bothered by this restriction. So it should be easier, right? So after we consider the simpler version, that's our first round. Okay. In the second round, then we factor in. Okay. First round we do not factor it in. The first round, after we remove that condition, we just apply this general result directly, right? That's the general result. Yeah. So general result, n equals 17. So we apply the formula, the maximum number of inversions, 1/2 times 17 times 16. Okay? Yeah. Certain number. Okay? Yeah. That's the first round. Yeah. So it's pretty easy. Yeah, we get the first round. Now we're ready to do the second round. This time we factor in that condition. Yeah, so let's erase it. Okay? This time we assume this N9 is not in place. All right. So here, this in place, so we need to go back to this general solution here. Under what situation we get a general solution? Under what situation we get general solution? Okay, yeah. The solution is when the array when the array is in the descending order. Descending order, we get this maximum number of inversion. Yeah. So here, if I write x to the 17, yeah, suppose that it's the largest, okay, for convenience, discussion. We write it as the descending order. x9, x8, x1, okay? Suppose that's the descending order. Okay? Yeah. Let's assume the order, the values match their subscripts for convenience. Okay? Yeah. All right. So in the descending order, is this in place? X to x9 in place? Yes, right? Yeah. Yeah. So it's in place. You can see it's in place. That means we cannot take this number because x9 is in place. Okay? Yeah. So now we need to do modification to make it out of place. Okay? So the question is, how do you do the modification? Yeah, we need to change a little bit. Or we need to move x9 to a different location. You just move it. You can change its location, so you make it out of place. The question is where to move. Yeah, some student, I saw 2 or 3 students move to, switch with the first one or the largest one. Then that move caused many inversions, right? Yeah, because you move too far. You move x9 too far. Then that move would cause more inversions. Yeah. So the best way is you just make a local move. Switch with its adjacent. Okay? x8 or x10. Yeah. Only do the switch with one of its adjacent element. In that way, you only reduce the inversion by 1. Other inversions, you still keep them. Okay? You do not change other inversions. You only change this adjacent inversion. Yeah? You change it. You change one adjacent inversion. All the other inversions remain the same. Yeah. So if you make adjacent inversion, there are 2 possible adjacent inversions. Just one of the 2. You take one of the 2 adjacent inversions. Then your answer just one fewer than this largest number. -1. That's your answer. Okay? Yeah. If you use this way, if you use this analysis, then you can get the right answer. Okay? Yeah. Try your best to understand this whole process, because in the midterm I will give you a similar question. Yeah. Slightly different from this version. But you need to be familiar with all the details I explained here. Yeah. Yeah. First round, second round. Yeah. Here you can see this strategy is quite effective, right? Yeah. First round, solve a simpler version. Yeah. The second round, you add that small change back. So then you do some small modification. Yeah. So then you will feel much better. Yeah. Because your thinking is, step by step thinking. Yeah. You can understand much better. Yeah. All right. Yeah. So that's this question. All right. So it's just, right, Rohan. Yeah. So your understanding is correct. Just the general case, general maximum case -1. Okay, yeah. Adjacent, you can see adjacent swap only change the inversion number by 1. Yeah, try to think about that. Other inversions, there is no change. Other inversions, yeah. Here, let me assume we just do swap between x9 and x8. Okay. Now, it only changes this current inversion, but the other inversion related to x9, no change. Other inversions related to x8, no change. And other inversions without related to x9, x8, no change. You can see no other change. So only one change. Yeah. Yeah. So that's the, main point. Yeah. So you need to know all these things. Yeah. All right. Let's move to the next. Yeah. I need to look at the time, but even we run out of time. So here I can only do one more question. Yeah. I don't know. So why I spend so much time? Yeah. Anyway, first I will post the full solution. Yeah. But even I post the full solution with the work, containing the work. Yeah. I still like to, use videos to explain the details. Yeah. To help you understand it better. Yeah. And remember, for the part B, 15 questions. You have 1 day grace period if you need it. Yeah. All right. Next question. Yeah, this one. Yeah, the answer. First, let me tell you the answer. Answer is 3. Yeah, neither maximum nor minimum. The answer is 3 comparisons. But there are so many students give me a very large number. So 100 something, 200 something, 3, several hundred. Yeah, you don't need that many, only 3. Okay, yeah. So here, we need to find some element. Yeah, xi that is not equal to maximum, and some xi and not equal to the minimum. Not equal to, that much easier. Yep. Why those students give me several hundred? Because they find the maximum and the minimum first, then too many. Okay. So those students, they find, if you find max first, and you need a 245, right? Yeah. Then you find the minimum. Then some more, right? Yeah, but some students may, try to improve finding both maximum and minimum. So we have an optimal solution so that 3n over 2, use this formula. You can do slightly better, but still several hundred, right? Still several hundred. Yeah, yeah. The problem is, because you need to find which one max, which one minimum, then there are too many. So if you do this way, too many comparisons. But if we do the negation version, we don't need that many. Negation version, because if we compare, so here we assume distinct element. Okay. Distinct element. So if we just do one comparison, let's say if we do x1 less than x2, only one comparison, we can get the information already. x1 cannot be the maximum, and x2 cannot be the minimum. You see? One comparison, we can get this much information, and it's almost there. You can see, yeah, because in our goal is the same element here, different element x1, x2, two different elements. One not equal to max, one not equal to min. But our goal, we want to get the same element that's not max, not a min. Okay. But not far away, right? Pretty close to the destination. Yeah. So you can see we just need a little more work. So we can get to the destination. Yeah. All right, so here. To get a little more work. So we just need to find one element that is greater than one element and smaller than another element. That's enough. Okay? So we only need to find one element that is greater than let's say x1. So say x1 just one of the elements greater than x1 and less than let's do not use x1. Okay, xj and less than xk. Okay, then we solve the problem. One element satisfy these two conditions, then we solve the problem. All right? Yeah. Then here you can see in this statement we only mention three elements, right? So one element. So that's our solution element. Let's say xi. Okay? xi. We only mention three elements. Then greater than another element we call xj. Okay? And less than the third one, xk. We only mention three elements here in this statement. How about, from this observation, how about we just select arbitrary three elements from the array. Three elements. Select arbitrary three elements from array. Yeah. So for simplicity, we can select x1, x2, x3. Okay. That's good enough. Yeah. We only need three. All right. After we select three, can we sort it? Can we sort it? Yeah. And we sort it with three comparisons. Yeah, we know that. We just need three comparisons to sort it. Let's assume x1 less than x2 less than x3 after the sorting. Okay. Then the one in the middle, x2, satisfy the requirement, right? x1 greater than x2 greater than x1 and x2 greater than x3. That means x2 cannot be the minimum, right? x2 cannot be the minimum. And x2 cannot be the maximum. And that's the solution. That's the solution. Okay? So you just pick three elements and sort it. The median, the median, the one in the middle, it's the median. The median is the solution, is one of the solutions. You can have many solutions. The median is one solution, one of the solutions. So then you solve this problem. Okay? Yeah? Yeah. So think about this question. Yeah. Here you can see understanding. Yeah. Why we can get this good solution. Three. Based on our understanding. If you go the wrong way, so if you want to find what is the maximum, what is the minimum, that's the wrong way. Yeah. So you waste too many comparisons. Okay, hundreds of comparisons. Too much. All right? All right, so I need to stop right here. Yeah, so I still have several questions. So let me just post my solution file first, so you can study. Yeah. Then when you study, so I will post a video for the remaining questions one by one.